So for our last class, I want to explain a little bit of this picture about this linearity approach and the transcendence approach in a context that goes beyond Andre Oort. So we'll talk about some work of Pila and Habeger and Pila, on the Dilbert-Pink problem in the modular context. So I want to talk about a rather special formulation of it. So we'll start with the curve C in x1 to the n. Actually, let me just simplify it straight away. Let's start with the curve C in x1 to the 4. And we'll define P and N to be the set of points x1, x2, x3, x4. So the first two are isogenously of degree m, and the second two are isogenously of degree m. So in other words, I want x1, x2 to be Pn, and x3, x4 to be Pm. So this is some set of special subvarieties of x1 to 4 of codimension 2, because we're encoding two relations. It's not all of them. You can also just take 3 coordinates and insist they're all pairwise isogynous, or you could make some coordinate special, but just for concrete, let's restrict to this case special variety, which are the most sort of interesting ones anyway that show up. Okay, so the conjecture, which is still open, so this is a special case of Dilbert-Pink, is that if the union over all m and n of the intersection of these special surfaces with this curve is infinite, this is precisely a Dilbert-Pink condition, right? This is dimension 1, this is called dimension 2. You expect them not to intersect. If there's infinitely many counterexamples, something should happen. In particular, then C is contained in a special subvariety. In fact, so either C is contained in something of the form Tn cross x1 squared, or C is contained in something of the form x1 squared cross Pm. Okay, so either the first two or the second two coordinates of C satisfy some constant isogeny relation. Okay, this is exactly an instance of Dilbert-Pink. Essentially looking for curves, so it's still open. So I want to describe the proof of Habeger and Pila of the following theorem. This is true if, so first we'll assume that C is defined over Q bar. This can actually be removed using work of Bombieri, Messer, and Zanier. They showed that the Q bar case implies the general case, quite generally, but we won't talk about that. So true, if this is true, and the curve is asymmetric. So what does asymmetric mean? It means if di is the degree of the projection of C into x1 via the ith coordinate, you have 4 such projections, they each have a degree. then we're assuming that all of these are unequal. So di are all distinct. So it's a somewhat technical condition. The curve, I guess in some sense most curves are asymmetric, but it's not really clear in which sense that is. So for symmetric curves, as you still open it, you'll see in the proof precisely where this kind of condition is required. Okay. Yes, I want to sketch the proof because it's sort of it definitely follows the same style we've been discussing, using homogeneity and transcendence for the Andrew conjecture and length conjecture, but it's applied in somewhat different ways. So let's first assume the contradiction is false. So assume the conclusion is false for contradiction. Then, by what we said, I think 2 lectures ago about monodromy, then if you look at the monodromy of C, you look at its map into SL2 Z to the n, and you take its Zariski closure, you get the entire proof. SO2 R at the end. Just from conclusion not being true. This might contain a special variety.
So is there something special about 4 here, or is the theorem?
No, the theorem is really can be still is for n,
okay.
and then for any 2 coordinates. Yeah, but I just want to give a very concrete. Sorry. 4 is here. That's why you're getting confused. I see. Yeah. I don't want to take care of all the combinatorial reductions. Yeah.
Oh, yeah.
4 is the essential case. Okay, so what we want to do again is bring in some sort of Pilawoki statement at some point, but we don't have any CM points in sight anywhere here, so we can't sort of apply it to our special point, against rationality that way. So instead, we observe that if 2 guys are isogynous in X1, and you live in the upper half plane, then there's some matrix with rational coefficients which takes the preimage of one to the preimage of the other. And that's where we're going to get our rationality from. Okay? So let's define Y alpha beta to be the set of Z1 through Z4 such that Zi's are in the upper half plane, and Z1 is alpha Z2 and Z3 is beta Z4. And this can be defined for any alpha and beta in SL2R. Okay. And now, as usual, we're going to define V to be the preimage of C from X1 to the 4th, to the 4th power of the upper half plane. And we're interested in when Y alpha beta intersects V. And we're going to put in the fundamental domain as well, just because we want definability, and without that, we can't get definability. So what we're going to look at so first we're going to make the following claim. That Y alpha beta intersects V in the fundamental domain up to the 4 is finite. for all alpha and beta. Okay, so again, we have definability. This thing is definable inside Rn x because this guy is algebraic, so it certainly is. So if it were infinite, it would have some dimension. So if not, would have real dimension at least one. However, both of these guys are analytic varieties. And so therefore, we have analytic dimension at least one. But V is already one-dimensional. Comes to the primitive curve. So for these guys, intersection 1, what we conclude is that V is inside Y alpha beta. No, by the way, this is going to end up being easier, but it's not X Lindemann. X Lindemann is an algebraic guy contained inside the primitive of a different algebraic guy. This is an algebraic guy upstairs containing the primitive of an algebraic guy downstairs. So it's reversed. It's not the X Lindemann assumption. Okay, so this is so this part here, this first part, is by definability. Because I try to define all in R next. Okay, so V is contained inside Y alpha beta, and now the idea is to use monodromy to say it is basically possible. So Y alpha beta is algebraic. So in particular, what we learn is that there's a risky closure of V inside C to the n, inside C to the 4, I apologize. It's not all of C to the 4, because in particular it's contained inside Y alpha beta. But V is invariant under phi of pi 1c with the monotomic group upstairs. And so with the risky closure, which is a natural thing associated to it, is also invariant under phi of pi 1c. Well, this guy is algebraic. So the thing that it's invariant under is also Zariski closed. And we showed that this is SL2R to the 4. Okay, and this is a contradiction. Because this X transitively in C to the 4, so the Zariski closed must be all C to the 4, which we assume is not the case. Okay? So far, that is the general statement about varieties under covering fluid. We haven't dealt with the zero big part of it very much yet. Okay, so these guys are finite for all alpha beta. So as an immediate corollary, there exists some constant they're not used. Let's say I want to use little c. Well, it's so difficult. Delta 1, I don't know, such that for all alpha and beta, the size of this is bounded by delta 1. In other words, it's uniformly finite, not just finite. So again, this would be just a trivial consequence of homonormality, which is very useful for things like this. So if you look at the family, and you write this properly. So if you look at the family, union over all alpha and beta of the pair alpha beta, you write alpha cross the singleton beta cross the set y alpha beta intersect v intersect f to the 4. This is inside SO2R squared cross, let's say h to the 4. And you can think of this parameterizing a family over SO2R squared, where the fiber over each alpha beta is exactly its intersection. So this is all definable. Every set here is definable, and the maps are definable. And so this family of intersections is a definable family over a definable base, as we showed in our work on homonormality. Whenever you have something like that with finite fibers, the fibers are in fact uniformly finite. Okay. So this is like quote unquote free using homonormality. It's pretty amazing, right? I don't know how well someone proves something this that it's uniformly finite. Okay. Yeah, uniform. Okay, so now we have the following lemma. Let me call it lemma G for Galois. This is the regular statement about Galois orbits being large. So the following thing. So if x1, x2, x3, and x4 is in C intersect our curve T and N, which is an isogeny here at degree M and here at degree N, and this 4 points are in C. And C is asymmetric, that'll be important. Then the degree of the field you get, sorry, these are x's, by adjoining the 4 coordinates has to be relatively large. At least the max of nn to the delta, where delta is some constant of phase, beginning of time. Okay? So in other words, the degree of the intersections has to grow at least polynomially in the isogeny relations defining the intersections. This will be some source of Galois-Wilkiness input for us, which as always will come from some Galois orbit condition. All right, so let me for now leave this unproven. I'll prove it at the end. These kind of things are very hard in general, and this is exactly the statement that's missing for the non-asymmetric case. We have a statement, this is the proof would carry over in exactly the same way. And it's also, statements like this are what's missing from the case where C is not a curve, but a surface and stuff like that. So we'll talk about that a bit as well. Okay, but for now, assume lemma G. And let's conclude. So, we want some growth, again. I'm going to come from the following place. This would be a subset of SO2R squared of alpha and beta where they're defined just so that this guy is not empty. Just looking at real alpha and beta, such that the surface y alpha beta intersects this holomorphic curve. Okay. So now that X is quite large, actually. I mean, this is real dimension 4. This is real dimension 2. We're in real dimension 8 space. So it should be a codimension 2 condition, basically. This is a 6-dimensional real thing, and so you expect it to be a codimension 4. And a total dimension 4 kind of space, which isn't. X will have real dimension 4. I'm not going to prove it, but keep in mind, X is actually quite large. Alright, so claims a tiny bit messier than the ones we usually have. It's not quite true. We can show that X has a lot of rational points, but it's not true at the number of integer points that X has grows subpolynomially in P. This is what we need for the Tilly-Wilkie machine to get going. To get semi-algebraic curves in X, all we need is for this to be false. Okay, so the idea is just to say that if we have one such point, then we must have many such points because Galois orbit is large, and then use that to get many points inside of X. So, if, let me call it X arrow, is in C intersect Tmn, then by lemma G, the size of C intersect Tmn is at least L to the delta. Write L for the max of M and N. Okay. Okay, and now for each, we call it X prime, inside Tmn, we can lift to Z prime inside V intersect F to the 4. And what do we know about Z prime? Well, we know it's in V intersect F to the 4, and we know that Z1 and Z2 have a degree m isogeny between them, and Z3 and Z4 have a degree n isogeny between them. So we know that Z prime 1 and Z prime 2 are isogenous of degree m. And from this it follows that there exists alpha inside. This is really, I apologize, this really be inside GL2. For the reason I mentioned earlier, which is that the matrix M001 is in GL2Q, but it's not in SL2Q. So that's sort of bad. So we really want this. There exists alpha in GL2Q with determinant alpha equals m, and you can show that they're both fundamental domain. You can actually have the coefficients of alpha to be not very large. So the height of alpha be bounded above m, such that m alpha Z1 prime equals Z2 prime, and likewise for beta. Okay? In other words, we get alpha beta in sort of x cubed of height at most L. Alpha is bounded by M and beta is bounded by M. Okay, so the potential enemy facing you here is that you had many points downstairs. Each one of those points gives you some alpha and beta, but potentially they all give you the same alpha and beta until you get 1 point. Right? But remember, we showed that any given alpha and beta gives you at most a fixed number, delta 1, of points. And so at most, delta 1 of these x primes can give you the same alpha and beta. And so therefore, the number of points in x of height L is at least the number of these x primes divided by delta 1. This is a fixed number. So this is at least multiple delta every 1. Okay? There's two parts to the argument. So the first part is to get many of these Galois orbits, and therefore many pairs of sort of point downstairs together with alpha beta upstairs, and then you show that for every point there's at most finitely many alpha and beta, a fixed finite number, and so that actually translates directly into many alpha and beta upstairs. Okay? Yes, it's a very different use of the Pidon-Wilke theorem because we're working inside of the group now instead of inside of the variety, or the symmetric space, as we did before. Okay, so X has many, or for the L's that occur like this, which is actually going to give you an L, and for those L's you have many integer points, so now Pidon-Wilke implies that X contains semi-algebraic curves Okay, so we're inside GL to Q, so we're actually going to apply the strong Pidon-Wilke, which sort of tells you about finding many families, yada yada, because we have to be careful, because you can always, like, if we're in GL to Q, you can always just scale alpha and beta and get a different alpha and beta. So that's sort of, you have to make sure you get the correct curve, but you can do that the way we have in triple that before. And so what you get, again, by analyticity of everything involved, you get an algebraic curve W in SL2C squared such that X intersect W is a real dimension, at least one, or at least is infinite. Like this. And so from this, what you can get is that if you union over alpha beta in W of Y alpha beta intersect V, intersect S to the 4, and this is complex dimension 1, because every one of them gives you a point, so you get different points without liquidity, you must get some complex analytic thing. Okay, but this guy is actually algebraic and analytic, and so what you get is that V is contained inside the union of alpha beta in W of Y alpha beta. This is codimension 2, unioning over a curve, This is codimension 1. Algebraic guy of codimension 1. And so this is a contradiction as before. This guy is algebraic. Implies the risky closure of V is not everything, and we showed that can't happen.
Okay.
Any questions on this argument? All right. Let me say something about this lemma G. We haven't talked about how you prove these things very much, but it's in the spirit of the height inequalities we discussed at the beginning of the course. 11G. Okay, so the first step is sort of the most important. So for x1, x2, x3, and x4 algebraic points on C, we can define the height on C by using any of these coordinates. So this is the height of any of them.
So
Yes.
yeah, so one is have we used the asymmetry?
No,
Okay.
we're about to use it literally right now. Yes, that's right. So what you get is that the height, let me focus on x1. The height of x1 over d1, let me just write it this way, is equal to the height of x2 over d2 plus big O of 1. Okay? So again, we'll never discuss height in generality, but the idea for this is suppose you have y squared equals x cubed plus 1. You have some elliptic curve. Okay? Then it's true that the height, so adding 1 doesn't change the height very much, so this is certainly equal to the height of x cubed plus big O of 1, which means the height of y divided by 3 is the height of x divided by 2 plus big O of 1 in this context. So in general, the proof is exactly the same. You have to work a little bit harder with general polynomial equations. But it's always true that when you pull back height from P1, you get sort of the canonical height up to the degree of this one, whatever. Okay, so this is the point where we're using this asymmetry, is in this relation. So low log d1 is bigger than d2. The starting point is the following. You have these two heights that behave unequally. This guy is bigger than this guy. Okay, so now we need a couple of results. So remember that we're working inside x1 to the 4, so all of these points correspond to elliptic curves. And so you can now think about the heights that corresponding elliptic curves and do stuff that way. So we're going to get two inequalities. I'm not going to prove either of them. The first one is relatively easy. Second one is very difficult. So the first one says that because these two are isogynous with an isogeny of degree m, look at the difference in their heights. It's bounded by at most log m up to a constant. This is because they have an isogeny of degree m, you do nothing else, nothing about the curve C or anything like that. So you can't change the height that much by taking isogenies. Okay, so this becomes very powerful when mixed with this guy. Okay, because that implies that 1/2 log m is greater than or equal to r minus 1 height of x2 plus big O of 1 up to a constant of the height of x2. So this gives you an upper bound for the height, this is very small, this log of this number m. If this r were equal to 1, you would get nothing from this. Because for all you know, the heights might be equal and nothing is violated. Okay? So you use asymmetry that on the one hand, these heights are related in a very precise way, relative to these projections and their degrees. On the other hand, the heights have to be very close to each other because there's an isogeny between them. Okay, so we now know that the height has to be very small, bounded above by log. So all this so far is sort of doable, and now we come to the result of master and Woodhouse. Which says that we have two elliptic curves, effectively in Horizon, elliptic curves. And if they're isogynous, then the smallest degree isogeny between them has to be not very big. So it says that in this language, assuming, which is not a big assumption for us, m is the smallest degree of an isogeny from x1 to x2, the elliptic curve corresponding to x1, the elliptic curve corresponding to x2, m is bounded above by the max of the height of x1, and this is the crucial part, the degree of its field definition, the power of some big number a. We got a curve with small height, find your low degree number field, and it's isogynous to, this is a height of x1, degree of you get both of these, so you get both of these. x1 and x part. Yeah. So the heights are small and degrees are small, and the middle degree isogeny is also small. Or said another way, either the height or the degree has to be at least as big as the power of m. It can't be the height. The height is bounded above by log, which is much too small. So we conclude degree bounded above by this power of m. Okay? Very powerful trick. It's also how you end up getting lower bounds for Galois orbits in the underwood case. It's one of the major steps. Okay, so I'm asking you to swallow a lot of the ingredients. But modulo these ingredients, the proof is up, right? We exactly want to prove the degree is bigger than that's starting the power of 100, right? So to say a couple more words, we're making an assumption here that m is the smallest degree of an isogeny. It's not really a big assumption because you really only have one isogeny between elliptic curves up to scale, unless your elliptic curves have Cm. And so this basically gets rid of everything except for the Cm case. And then in the Cm case, things sort of, you switch it up, it becomes more like a Brior, it becomes a little easier. I don't sort of want to deal with that case. But this isn't a big assumption unless you have Cm, in which case you simplify it. Did I make any other assumptions? No, not much. I mean, I'm assuming these intersection points are in Q bar, but that's free as long as the curve is in Q bar. You guys are isolated. All right. See, I think it's very interesting to try and remove this asymmetric condition, which feels like it's the most unnatural thing in the world. But no, I've tried and failed. Okay, so just a couple of comments, so general comments. So we can ask about Zilber-Pink for, instead of C now, let's deal with an arbitrary variety in x1 to the n. With dimension bigger than 1. So then, as far as I know, nothing is known. Dimension bigger than 1, modular case. There are no results, unconditional results. There's lots of conditional results. But so how does the picture look? So first of all, so difficulties. So the major difficulty is the Galois orbits. Is that lemma G analogs are completely open. And they are hard to phrase, right? If V is some codimension, impose that many isogeny relations to get down to isolated points, and then conjecture that those points have large Galois orbits. You gotta then be a little careful for what happens if you have higher dimensions than expected intersections and things like that. But just the base case is enough to get you going. So it's the state, but there's no methods, and even sort of not really, I haven't seen these special cases even because the trick of using the coordinates to define the height doesn't work in general. For a surface, you need 2 coordinates to define the height, and somehow it becomes very awkward to think about it. So that's the major difficulty of the proof. So assuming lemma G analogs, what would happen if we assume this kind of thing, we would get that X, the similar variety of X that we define in this proof, which is defined as similar variety general, contains semi-algebraic curves like before. But before, we had a curve be dimension 1, so as soon as something intersected in dimension 1, it contained it. And that became really nice because it's easy to deal with. That's no longer going to be true. We're not going to have algebraic guys just intersecting the pre-image of our variety. And so we conclude that we have algebraic W in H to the n such that W intersect the pre-image of this guy is atypical. So the proof now is not true that W will contain this guy, it's just true that the dimension of the intersection is larger than you would expect for trivial dimension reasons. And so, because of that, you need the X-general theorem. Which just tells you from transcendence reasons that as soon as this happens, so something weird is going on, some special guy in play. And once you have X-Chanual, then you can sort of, assuming these kind of analogs, take the proof forward. So there are results which say that if you have sufficiently many analogs of this, maybe some similar things for heights, you need some upper bounds for heights, I think, as well, which are of this flavor. Then using X-Chanual and this proof technique, you can sort of make the whole thing go through. All right, I think that's the end. Thanks very much for listening.